Hello. In this video, we are going to again discuss the Diels-Alder reaction. Specifically, we are interested in the orientation of the dienophile. We already know that the diene is required to have the S-cis conformation. But what about the dienophile? For our first example, we are going to look at the case where our dienophile is a cis conformation of 2-butene. We know that we are going to have a 6-membered ring form, but what about the 2 methyl substituents which are cis in the dienophile? We show the forming new sigma bonds are shown in green, and we get, again as we've seen before, a 6-membered cyclohexene ring where we have a 4,5 dimethyl substitution. But more than that, since we started with a dienophile with both substituents on the same side, in the product they are also on the same side, and to show that they are nearer to us than the plane of the ring, we have shown them as wedges. So if we start with a cis dienophile, we end up with a cis cyclohexene ring. Here we see the computed transition state for the Diels-Alder addition of 1,3-butadiene to the cis 2-butene. Here is the di-substituted product with the hydrogens omitted to make it easier to see the carbon skeleton. Notice that since we have a cis substitution, one of the methyl carbons is going to be in an axial position and one is going to be in an equatorial position. On the other hand, let's suppose that our dienophile is now a trans 2-butene. We notice in the product that forms, we again get the cyclohexene ring, but now one of the methyl substituents is closer to us, and one is further away than the plane of the ring. So therefore, now we have a trans substitution on the cyclohexene ring since we started with a trans dienophile. Here is the computed transition state for the addition of 1,3-butadiene to the trans 2-butene. Here is the carbon skeleton of the product trans 4,5 dimethyl cyclohexene with the hydrogens omitted for clarity. In this view of the product, it is easier to see the trans positions of the methyl groups. We see that they are now both in axial positions. Our next dienophile is a cis-substituted dicyanoethylene. It is very common in dienophiles for them to feature electron withdrawing substituents. And here we see we have a di-substituted with the very powerfully electron withdrawing cyanide group. Since we started with a cis substitution, again we notice now that when we form our product, the cyano groups are both nearer to us than the plane of the cyclohexene ring, so therefore they are cis substituted in the product as well.
Here we have two consecutive views of the computed transition state for the addition of the 1,3-butadiene to the cis dicyanoethylene. Note here that we have strongly electron withdrawing groups attached to the dienophile. Here we have two consecutive views of the product, which is a cis 4,5 dicyanocyclohexene, showing the cis relationship of the cyano groups, one of which is in an equatorial position, the other of which is in an axial position. In this particular diagram, we see the hydrogens removed for the sake of clarity.
If we now have the trans-substituted dicyanoethylene as our dienophile, we notice that, again, the substituent pattern in the product is going to be trans with respect to the two dicyano groups.
Here we have two views of the computed transition state for the addition of 1,3-butadiene to the trans dicyanoethylene. The next three diagrams show the computed product, the trans 4,5 dicyanocyclohexene. We can see clearly, particularly in this diagram, that both of the cyano groups are in axial positions. Here we see in a side view, we can see the opposite arrangement, both axial, of the cyano groups. In Table 2, we see the calculated enthalpies of activation and reaction for the reactions shown in this video so far, as a comparison to the Diels-Alder addition of 1,3-butadiene to ethylene. And we notice a couple of things here. One is that for the 2-butene, that there is a considerable difference in the energy of activation between the cis and trans version. Also, we see that when we add a strongly electron withdrawing group to the ethylene group, the cyano group, that the energy of activation is much smaller than it is for a methyl group. This will be a continuing theme that we will explore further in future Diels-Alder videos. I thank you very much for your attention, and as always, have a good one.